Dear student, warm welcome to NPTEL Phase 2 video course on Geosynthetics Engineering in Theory and Practice. This is lecture number 30. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This is module number 6, lecture number 30, Geosynthetics for Reinforced Soil Retaining Wall. Now, I will show the recap of the previous lecture. That is, we covered the example design of GeoGit reinforced soil wall under static loading. We have also covered the different coverage ratio, and 4 cases have been considered where the shear value is equal to the 1 with the length remain the constant, and shear value is equal to 0.6, the length remain constant, and shear value is equal to 0.6 with varying the length of the reinforcement, and shear value is equal to 1 with varying the length of the reinforcement. And we have optimized and most economical and stable design have already been covered with the different example. Now, I will focus that stability problem where the check for the seismic stability. Seismic loading condition, what will happen this reinforced soil wall. You can see here, this is the same wall, this is 15 meter height, and it is the varying length of the reinforcement. And in case of the seismic, and this force will be acting the 2/3 or 0.6 times the height of the wall. So, we have to be considered into this design. Now, for seismic thrust PAE is equal to 0.375 alpha m into gamma b into h square. We know this equation, what will be the seismic thrust, where alpha m is equal to 1.45 minus alpha 0 into alpha 0, where alpha of 0 is the basic horizontal seismic coefficient, that is 0.05 given for the zone 2. So, India had the different zone, zone 1, zone 2, zone 3, zone 4, and you have to be careful for the selection of the basic horizontal seismic coefficient, that is alpha 0. Let us say for the zone 2 where basic horizontal seismic coefficient is 0.05, and gamma b unit weight of the backfill soil is 17.5 kilonewton per meter cube, and h is equal to height of the reinforced wall, that is 15 meter. So, from the equation that alpha of m is equal to 1.45 minus alpha 0 into alpha 0, we know now from the zone that alpha 0 value is equal to 0.05. So, you are substituting this value of alpha 0, that it will be 1.45 minus 0.05 into 0.05 is equal to 0.07. So, ultimately we have to calculate what will be the seismic thrust, that is PAE, that is PAE will be equal to 0.375 into alpha m, we calculated 0.07, and gamma b we know that unit weight of the backfill soils, that is 17.5 kilonewton per meter cube into h is equal to height of the reinforced wall, that is 15, here h square will be the 15 square. So, we can write 0.375 into 0.07 into 17.5 into 15 square, that is 103.36 kilonewton per meter. That what is the seismic thrust. So, we know that what is seismic thrust PAE. Now, what will be the horizontal inertia force, that is PIR. So, PIR is equal to alpha m into gamma r into h into L maximum. Here L maximum is the length of the reinforcement, that is 10.5 meter, and gamma r is the unit weight of the reinforced soil, that is 18.5 kilonewton per meter cube. But horizontal inertia force, you have to keep 50% of PIR should be considered. So, what is PIR? So, PIR, from the equation alpha m gamma r h into L max, you substitute the value. Alpha m we know 0.07, gamma r is equal to 18.5 and h is equal to 15 and L maximum is 10.5. So, PIR value will be 203.96 kilonewton per meter. So, this is horizontal inertia force. Here, in case of horizontal inertia force, you have to consider 50% of the PIR. So, total dynamic force on the retaining wall FD will be equal to, we have calculated what is PAE plus 50% of PIR. So, that means 103.36 plus 0.5 into 203.96 kilonewton per meter, that means 205.34 kilonewton per meter. Now, this FD will act at a distance of 0.68 from the bottom of the wall. As I showed you earlier, that this force will act 0.6 times the height of the wall from the bottom of the wall. Now, what is overturning moment due to the dynamic force, that is MOD. MOD will be equal to the total dynamic force FD into 0.68, that means 205.34 into 0.6 into 15, that means 1848.07 kilonewton per meter. This is overturning moment due to dynamic load. Now, you have to check for the sliding. Total driving force including the dynamic force F total will be equal to F of static plus F of dynamic. F static, it is 727.44 plus F dynamic 205.34 kilonewton per meter, that will give 932.78 kilonewton per meter. You check what will be the total resisting force R, which we have calculated earlier. It is 1578.815 kilonewton per meter. So, factor of safety against sliding is equal to R divided by F of total, that means 1578.815 divided by 932.78, that means 1.693, that is greater than 0.75 into 1.5, that means 1.125, that means safe. So, this is 75% of the what will be the factor of safety for the static case. So, it is satisfying the criteria. So, you have checked for the sliding. So, it is okay. Now, check for the overturning. Total overturning moment including the overturning moment with due to the dynamic force MO total will be equal to MO static plus MOD for dynamic. So, that is 4105.35 plus 1848.07 is equal to 5953.416 kilonewton per meter. Similarly, total resisting force MR, which we have calculated earlier, that is 20855.09 kilonewton per meter. So, factor of safety against the resisting moment will be equal to MR divided by M0 total. That means 20855.09 divided by 5953.416 is equal to 3.5, that is greater than 0.75 into 2 is equal to 1.5. So, we check against the overturning and it satisfies this criteria due to seismic loading. Similarly, you can also check for the bearing capacity as the wall is safe against the bearing capacity failure. For the static case, it is the safe even considering the seismic condition. Now, we will give one example, that is designed for precast segmented block retaining wall of height 8 meter with geogrid as reinforcement. In this problem, it is given that coverage ratio, that is CR is equal to 1, length to height ratio L by H greater than equal to 0.7, that is L should be greater than equal to 5.6 meter. Surcharge load Q is equal to 18 kilonewton per meter square. Allowable tensile strength of the geogrid T allowable 38 kilonewton per meter. For connection of the geogrid with segmental block connection strength TC is equal to 34 kilonewton per meter. Interaction coefficient Ci is equal to 0.85 and foundation bearing pressure is equal to 700 kilonewton per meter. So, these are the some parameter is given. Apart from that, here properties of the backfill soil is given, that is angle of internal friction of the backfill soil pi b is 33 degree. Unit weight of the backfill soil gamma b is equal to 18 kilonewton per meter cube, and properties of the reinforced soil, angle of internal friction of reinforced soil pi r is equal to 24 degree. Unit weight of the reinforced soil gamma r is equal to 20 kilonewton per meter cube, and foundation soil properties, angle of shearing resistance between soil and the reinforcement, that is delta r is equal to 26 degree, cohesion is 0 kilopascal, and also bearing capacity of the soil is equal to 700 kilopascal. So, this is the wall you are to design, and this height of the wall is equal to 8 meter, and here is the surcharge load 18 kilonewton per meter cube, and this is the bearing capacity which is given about 700 kilonewton per meter, and this is the properties of the foundation soil, this is the properties of the backfill soil, and this is the properties of the reinforced soil zone, and this is the precast concrete segmented block, and this is number of the layer of the geogrid. So, now we have to go for solution. A, external stability. Step 1, calculation of coefficient of earth pressure for backfill soil. So, first of all, you have to calculate what will be the coefficient of. So, if this is the wall, this is the backfill soil. So, here you have to find out what is the K of AB, where pi of B is given. Pi B is equal to angle of internal friction of the backfill soil, which is given 33 degree. So, you can calculate that KAB from this equation, that is KAB is equal to 1 minus sin B by 1 plus sin B. So, sin pi B value is given 33 degree. So, KAB is equal to 1 minus sin 33 divided by 1 plus sin 33, that is 0.294. So, you know KAB, that coefficient of earth pressure of backfill soil 0.294. Now, we calculate the horizontal driving force due to the backfill soil and the surcharge. Here you can see that this is the horizontal earth pressure due to backfill soil. This is the horizontal earth pressure due to backfill soil, and this is the horizontal earth pressure due to the surcharge load. So, this load, it is force is acting is P1 at a distance of H1 from the base of the wall. So, H1 is equal to H by 3 if the height of the wall is H, if height of the wall is 8 meter. So, this small H1 will be equal to H by 3 is equal to 2.66 meter, when the horizontal earth pressure due to the backfill, that is P1. What will be the horizontal earth pressure due to surcharge is P2, and which is acting in the middle of the wall, that means h by 2. That means small h2 is equal to h by 2 is equal to 8 by 2 is equal to 4 meter. So we know that what is h1 and what is h2, we know what is p1 and what is p2 and what it is the acting. So horizontal, we have to calculate what will be the horizontal driving force due to backfill soil, that is P1. So P1 is equal to 0.5 KAB gamma B into H square. This is P1. We know KAB, coefficient of earth pressure of the backfill soil, we calculated 0.294. Gamma B, unit weight of backfill soil given 18 kilonewton per meter cube, height of the retaining wall 8 meter. So you calculate P1 is equal to 0.5 into KAB is 0.294 into gamma B is equal to 18 kilonewton per meter cube into height is equal to 8, then 8 square. So it will give P1 value is 169.34 kilonewton per meter. That is the horizontal driving force due to backfill soil. Now similarly, what will be the horizontal driving force due to surcharge, that is P2. So P2 is equal to Q into KAB into H. So Q is equal to surcharge load, which is given 18 kilonewton per meter square. KAB is known 0.294, height is known 8 meter. So P2 you can calculate is equal to Q is equal to 18 into 0.294 into 8 is 42.33 kilonewton per meter. So we know that what is P1 and what is P2. So we can calculate step 3, what is the total horizontal driving force. So total horizontal force P will be equal to P1 plus P2. So P1 I say horizontal force due to backfill soil is calculated 169.34 kilonewton per meter, and P2 horizontal force due to surcharge is 42.33 kilonewton per meter. So total horizontal driving force P is equal to 169.34 plus 42.33 is equal to 211.67 kilonewton per meter. Step 4, calculations of resisting force. So here you can see here, this is the W, what is the total weight of the reinforced soil, and here the wall moves. This is a segmental block retaining wall. Wall wants to move and it should be resisted. This is due to the sliding. And if weight of the reinforced soil is W, and it will be resisted by mu of W. So this is mu of W. W is equal to total weight of the reinforced soil. And total resisting force will be mu of W. So mu is equal to the static coefficient of friction. And for the W, you know what will be the length, what will be the height of the reinforced soil, and you know what will be the gamma or R, unit weight of the reinforced soil zone. So you can calculate what will be the W value. So we can calculate the resisting force. You can see mu is equal to tan of delta F. Delta F value is given 26. So tan 26 is equal to 0.4877. And weight is equal to, I say gamma into H into L, 20 into 8 into L. So what delta R is equal to angle of shearing resistance between soil and the reinforcement, that is 26 degree. And gamma R is the unit weight of the reinforced soil, that is 20 kilonewton per meter cube. H is equal to height of the retaining wall is equal to 8 meter. L is equal to length of the geogrid. So total resisting force is equal to mu into W, that means mu value is 0.487 into that W is equal to the 20 into 8 into L. 20 is the unit weight of the reinforced soil, 8 is the height, let us say it is the L. So you are keeping the total resisting force in terms of the length. So that will be 77.92 into L kilonewton per meter. Now step 5, you have to check for the factor of safety against the sliding. And you consider minimum factor of safety against the sliding is 1.5. So we know the factor of safety is the ratio of resisting force and the sliding force. So what is resisting force? Resisting force we calculated, that is 77.92 into L kilonewton per meter, and driving force is 211.67 kilonewton per meter. So hence we can write that 1.5 is equal to 77.92 into L divided by 211.67. So from there you can calculate the L. The L value is equal to 4.068 meter, which is less than 5.6 meter. That means 5.6 meter means that is 0.7 times the height of the wall. Height of the wall is 8 meter. So it is less than 5.6 meter, mean okay. So therefore adapted length of the geogrid should be 5.6 meter. Now step 6, you have to calculate the length of the geogrid based on the overturning. Now there is a possibility for the overturning. So you have to check up what will be the factor of safety against this overturning. So factor of safety overturning is the ratio or the stabilizing moment and the overturning moment. So you have to calculate what will be the minimum factor of safety against the overturning. Let us consider minimum factor of safety against the overturning is 2. And this is the weight of the reinforced soil, and L is the length of geogrid in the reinforced soil zone, and there is a leveling pad, and you have to take a moment at the toe of the wall. So we need the stabilizing moment, which is designated as MS. MS is equal to W into L divided by 2, because this resisting moment which is acting at the middle of this wall, this is W and this is length L. So this you take a moment at the toe, that W into L by 2. So this is W into L by 2, that is stabilizing moment. So W is again is equal to H into gamma R into L, and H value is 8 meter, gamma R value is 20 kilonewton per meter cube, and L is equal to length of the geotextile. So you can calculate the MS in terms of the length. So MS is equal to 8 into 20 into L square divided by 2. This will give the stabilizing moment MS is equal to 80 into L square kilonewton meter per meter. So then overturning moment. So you have to calculate the overturning moment, that is M0. So overturning moment, if you can calculate, suppose this is the P1 force, that is horizontal force due to the backfill. So this P1 and this distance H1 is known. So P1 into H1 horizontal earth pressure due to the backfill soil. Similarly, this is the P2. So P2 into H2, that is horizontal pressure due to the surcharge. So you take a moment at the toe, that is P1 into H1 plus P2 into H2. So what P1 is equal to horizontal force due to the backfill soil, and P2 is equal to horizontal force due to the surcharge soil. And you know that H1, that is the distance of the horizontal force P1 from the base of the wall, that means H by 3, that means height of the wall is 8, so 8 by 3. And H2 is the distance from the horizontal force P2 from the base of the wall, and height of the wall is equal to 8. So small h2 will be equal to h by 2 is equal to 8 by 2 is 4 meter. So hence you can calculate what will be the overturning moment. Then overturning moment will be equal to P1 you have calculated earlier, 169.34 into 8 by 3 plus 42.33 into 8 by 2, which will give the overturning moment is equal to 620.8 kilonewton meter per meter. So you know the overturning moment. So you have to calculate what will be the factor of safety against this overturning. So factor of safety against overturning will be equal to MS by M0. So you know that factor of safety we consider 2. You know factor of safety against that MS is value is 80 into L square. This divided by MO is 620.8. So L you can calculate, and that L value is equal to 3.93. So L is equal to 3.93 meter, which is less than 5.6 meter or 0.78. Therefore, you adopt the length of the geogrid is 5.6 meter. Now, step 7, you have to check for the bearing pressure. then factor of safety again is bearing capacity, that is the ratio of allowable bearing pressure by actual bearing pressure. Now, allowable bearing pressure is given in the problem, that is 700 kilonewton per meter square. Now, you can see this is the wall, this is the reinforcement, and there is a possibility for the failure due to the bearing capacity. So, it is necessary to check the bearing capacity at this zone. So, if you want to check that bearing capacity, then what will be the actual bearing pressure? That is due to the load of the reinforced wall and due to the surcharge load by the acting length as per Mayor of pressure distribution, that is L minus 2E. I have shown you also the earlier. So, where H is equal to height of the wall 8 meter is given, L is equal to length of the geotextile input soil, that is 5.6 meter, and Q is equal to surcharge pressure is 18 kilonewton per meter square. So, you can substitute this all this value. Gamma R also unit weight of the input soil is 20 kilonewton per meter. So, you can substitute this value and check that eccentricity. Eccentricity is equal to overturning moment by total vertical load. That means E is equal to M0 by W plus Q into L. Where M0 overturning moment given 620.80 kilonewton meter per meter, and W is the weight of the reinforced soil behind the retaining wall, that is 8 into 20 into 5.6, that is 896 kilonewton per meter. Now, eccentricity E, if you substitute this value, this value M0 by W plus Q into L, that means M0 value is given 620.8 divided by this is calculated, Q value that also it has been calculated is about 896 plus that is that Q into L. Q is equal to surcharge load 18 and length of the reinforcement 5.6. So, eccentricity is 0.62 meter. Here E is equal to 0.62 meter, that means less than L by 6, that is 5.6 by 6 is equal to 0.93. Since the eccentricity value is less than L by 6, so no tensile will develop. That means it is okay. So, actual bearing capacity which we have shown you earlier, that gamma R into H into L plus QL divided by L minus 2E, this is active zone. Now, you know what will be the value of E is 0.62. So, you substitute this value 0.62 here, and gamma R is 20, H value is 8 meter height, L of the length of the reinforcement 5.6 plus Q surcharge load 18, L again 5.6, L 5.6 minus 2 into E, E is 0.62. So, if you calculate, you will have actual bearing pressure 996.8 divided by 4.36, that is equal to 228.62 kilonewton per meter. But in the problem, it is given the allowable bearing pressure is 700 kilonewton per meter square. So, you can check that factor of safety against bearing capacity, that is allowable bearing pressure by actual bearing pressure. That is factor of safety against bearing capacity 700 divided by 228.62, that is 3.08, and this is greater than 2, means it is okay. So, now B is the internal stability. Step 1, calculation of the horizontal pressure sigma HF at any depth. Maximum horizontal earth pressure sigma H maximum on the back of the retaining wall at any depth H due to the surcharge load Q and the backfill, also considering that measure of pressure distribution. So, we can obtain this equation, that is sigma H maximum is equal to K R into gamma R into H plus Q divided by 1 minus K B gamma B into H plus 3Q H by L whole square, this divided by 3 into gamma R into H plus Q, where K A R is equal to 1 minus sin pi R divided by 1 plus sin pi R. So, we will use this equation for the calculation of the horizontal pressure at any depth. Now, here that you know K R is 1 minus sin pi r value is given, that is internal friction angle of the reinforced soil, that is 34 degree. So you can calculate Kr 1 minus sin 34, 1 plus 34, 0.28. So Kr is equal to 0.28. Now Q of the surcharge pressure is given 18 kilonewton per meter. Kr is equal to active earth pressure coefficient of the reinforced soil. Gamma B unit weight of the backfill soil given 18 kilonewton per meter cube, and KAB active earth pressure coefficient for the backfill soil is 0.294. Gamma R unit weight of the reinforced soil 20 kilonewton per meter cube, and L is the length of the retaining wall, that is 5.6 meter. Now at any depth you have to calculate what will be the actual earth pressure, that is PHF at the facing. So at the facing, sigma HF will be equal to what will be the maximum earth pressure, sigma H maximum into RF, where RF is called the reduction factor. And this reduction factor can be determined with this equation, 1 minus 0.25 into capital H minus small h divided by capital H, where H is equal to height of the reinforced soil wall. At any depth you can calculate that H value. Suppose H value is 5 meter height, then you can calculate what should be the reduction factor. So if you know the reduction factor at any depth, then you can calculate what will be the actual horizontal earth pressure at the facing. So horizontal earth pressure at the facing, you know what will be the sigma H maximum, and then you know at that depth what will be the reduction factor. If you know the reduction factor, then you can calculate what will be the actual horizontal earth pressure at the facing, which is called the sigma of HF, and you know height of the wall H is equal to 8 meter. So with this equation for this wall, this is about 8 meter, at any depth you can calculate what will be the sigma maximum from this equation. You know what is the maximum of this equation, all these values are known to you. So you have calculated for sigma of H of maximum, and you are putting those values here. So what is sigma H maximum? And then you are calculating the reduction factor at any depth. If you take H, small h value is 3 meter, and if you know that small h value 3 meter and capital H value is 8 meter, so you can calculate what will be the reduction factor. So with this equation you can calculate reduction factor, here the reduction factor at various depth. So if you know reduction factor, then what will be the pressure at the facing, that is sigma HF. Sigma HF, you are using this equation, that sigma HF is equal to sigma H maximum into reduction factor. So you know sigma H maximum into reduction factor 0.75 will give you that what will be the pressure at the facing, that is 3.78. So on all depth you can calculate the sigma H maximum, you can calculate the reduction factor, and equally you can calculate what is the pressure at the facing. Now I can show you that what will be the relationship between the depth and the maximum pressure, what will be the depth between the what will be the pressure at the facing. So this the figure shows the variation of horizontal pressure with the depth. So this is 8 meter depth and this is the horizontal pressure. You can see this is the nature of the curve when sigma H is the maximum, and this is the relationship between the horizontal pressure with the height when it is at the facing. So sigma HF at the facing. So sigma H facing is less than the sigma H of maximum. So you can determine that what should be the maximum pressure and what should be the pressure acting at the facing. So this figure shows the variation of the horizontal pressure with the depth, how it is that increasing with this depth. Now step 2, calculation for the vertical spacing. So if this is the retaining wall and you have to calculate what will be the SB, that means what will be the spacing between the two reinforcement, and which is designated as S of P. Now if we call allowable tensile strength of the geogrid. So, allowable tensile strength of the geogrid is 38 kilonewton per meter is given. However, TA is equal to sigma H maximum into SB1 by C of R. Now, sigma H maximum is equal to maximum horizontal pressure kilonewton per meter square. SB1 is the vertical spacing based on the tension in the geogrid meter, and CR is the coverage ratio. Here coverage ratio is equal to 1. Therefore, SB1 will be equal to 38 divided by sigma H maximum. Next, connecting pressure between the geogrid and the segmental block, that is TC, is given 34 kilonewton per meter. However, TC is equal to sigma HF into SB2 divided by C of R. So, sigma S is equal to actual horizontal pressure kilonewton per meter square. Here SB2 vertical spacing based on tension in connection in meter, and CR is the coverage ratio is equal to 1. So, therefore, SB2 will be equal to 34 by sigma H. Now, here it is point to be noted that we are considering vertical spacing SB1 when based on the tension in the geogrid. There is a failure for the tension in the geogrid. So, what spacing you should consider? Or here SB2 vertical spacing based on the tension in connection. The failure may due to the connection or failure may due to the tension in the reinforcement. So, if the spacing is SB2, that is the vertical spacing based on the tension in connection, then SB2 will be 34 by sigma of H. Now, spacing you have to select minimum of SB1 or SB2, that is tension in connection or the tension in the geogrid itself. So, based on that you have to select the spacing, and whichever will be the minimum, either the SB1 or the SB2, but it should be less than equal to the 1 meter. Now, here this table calculation of spacing at different depth. This is 8 meter height wall, sigma H maximum, reduction factor already calculated. This is the pressure for the facing element. You can see that this is the SB1 and SB2. So, geogrid may fail due to tension or geogrid may fail due to the connection with the facing element. So, these are the facing, these are the spacing for SB1 and SB2. So, you have to select, I mentioned that it should be less than equal to 1 meter. So, you cannot adopt this. So, you can adopt this spacing between the reinforcement 1 meter, 1 meter, 1 meter and 1 meter, this also 1 meter, and this also you can approximately less than 1 meter, 0.5 meter you can consider. So, here also between the spacing and the depth for the defined value of SB1 and SB2, and with the depth I have shown the curve. You can see this is increasing, the depth is increasing, also spacing, and after certain times it is like this. So, whatever it may be, you have to be consider the spacing about the 1 meter or less. Step 3, calculation of anchorage length of the embedded length. Now, here this is the geogrid reinforced wall, and this is the length of the geogrid, and this is the embedded length, what is called LE, and this is the failure surface which is making at an angle of 45 degree plus pi by 2. So, at any depth Z you can calculate what will be the embedment length LE, and this spacing between the two geogrid is SB. So, for the embedment length we know that SB into sigma H, Fs pull out, that is 2 into LE into Ci sigma B tan pi dash into Cr. So, from this equation you can calculate LE is equal to SB into sigma H factor of safety due to pull out divided by 2 into Ci into sigma b tan pi dash into Cr. You know what is spacing, that is the spacing between the geogrid. You know sigma h horizontal stress kilonewton per meter, and this is factor of safety due to pull out, and that you assume that is 1.5, and this is the Ci, which is called interaction coefficient, and this value also given 0.85, and sigma b is the vertical stress, and this sigma b is vertical stress is equal to gamma r into h. So you know that gamma r at any depth h is known, so you can calculate the what is sigma b, and tan pi dash, which is pi r, that is internal friction angle of the reinforced soil, that is 34 degree, and Cr is the coverage ratio, that is 1. So now if you substitute all this value, then you can calculate the L of E, what is called the embedment length. So you know the embedment length, then you can calculate the what is the LR, that means non-acting or ranking length. So this LR, I am just showing you that so if this is the total length of the reinforcement is that L, and this is the, let us say, geo grid. So this length is equal to L of E, and this length is equal to L of A. Now this angle is 45 degree plus pi by 2. So this angle will be 45 degree minus pi by 2. Okay, so what we have done, that we have calculated what is L of E here with this equation. From pull out you can calculate that L of E. So LE value is known because you know all these parameters. So you have to calculate L of R. Okay, this is LR. So this LR you have to calculate. That means if the height of the wall is equal to h, so you are calculating at any depth. Let us say this depth is equal to z. So this height will be h minus z. This is from here to here h, here to here z, from where you want to calculate this L of R. L of R. L of R you want to calculate. That means this distance you want to calculate. So this will be h minus z. So L of R will be equal to h minus z into this angle, tan of 45 degree minus pi by 2. So you can write L of R, this is equal to h minus z, this is h minus z into tan of 45 minus pi by 2. This is tan of 45 degree minus pi by 2. So from this equation you can calculate LR value, that is non-acting ranking length at any depth. So from this equation you can calculate. So from this then you can calculate the total length, that is you know LE, you know LR, so total length can be calculated. So here in this table showing the number of layer, and this is the depth 0.75 spacing and mean vertical spacing, and here maybe spacing is given 1, 1, 1, 1 and 0.5, 0.5, 0.5 as I shown you earlier. And then you have calculated what is LE, that is embedment length, but embedment length you require 1 meter minimum, so LE, that is why I put 1 meter. And then you have calculated LR from this equation. So LR you have calculated this equation. So total length will be LE plus LR. So LE is known 1 meter, LR you know 3.85. So this plus this will give the total length L. So you know this is the total length. But you see that because the height of the wall is about the 8 meter, so this 0.7 times of the height of the wall, it will be the 5.6. So therefore L required is 5.6 is keeping constant for all the layers. Now here is that reinforcement detail has been shown. So this is the precast concrete segmented block, and this is length of the reinforcement, that is constant, and initially you know that how many spacing 0.5 meter up to this, and then again 1 meter like this. So geogrid has been placed accordingly. You are also to check for the seismic loading condition. I have already mentioned that how to check the seismic loading condition. So you can check the seismic loading condition from this. This another example that calculate the horizontal stresses with depth on a wall of 8 meter high under the 200 kilonewton tandem axial track with 8 wheels. You have to calculate horizontal stresses at 1 meter increment and plot the variation of maximum wheel load stress along the depth. Most of the time we do not consider that wheel load into the design. For the wheel load, what will be the pressure acting on the wall. Here with this example we will show you how and what kind of the pressure is acting on the wall. So this is the wall. This is precast concrete segmented block. This is the layer of the reinforcement. This is the leveling pad, and this is the 8 meter height wall, and there is also structural load. This is the wheel load. You can see here wheel load, and which is located at a distance of 1 meter from the facing of this element. Now what is the wheel load? Here it has been shown. Now this is the 200. So there are 8 wheel, 1, 2, 3, 4, 5, 6, 7 and 8. And this is the location for stress calculation. That means this is the vertical face of the retaining wall, which is located at a 1 meter from this wheel. And because there are 200 kilonewton, so each wheel will carry 25 kilonewton or 25 kilonewton. And this is the configuration of the wheel from this to this distance 1.45 meter, and here this distance between the wheel is 0.4 meter, this is 1.4 meter, again here it is a 0.4 meter, and you have to calculate that what will be the stresses here, and this is located at a 1 meter from this wheel, from the vertical face of the retaining wall. And this angle is 50 for the wheel load 2, this angle is 54.5 degree, this is 45 degree, this is 26.6 degree, and this is 23.6 degree. So these are all given. So, to calculate these traces, we have to adopt some equation, that is NAVFAC DM 7.2 Bureau of Yard and Dock US Navy April 1982. So, here is the pressure distribution according to the Boussinesq equation, and here Qp is the point load, and this distance x is equal to mh, and here that is z is equal to nh. This you have to remember, what x is equal to mh, what z is equal to nh, and point load is Qp, and this is the pressure, that is sigma of h. If you take a section, you can have of section AA, and here Qp is the point load of the wheel at an angle theta here. So, this is the wall sigma h. So, where this is equal to x, okay. And if you want to calculate what is the sigma of h dash, sigma of h dash will be equal to sigma h into cos square into 1.1 theta. And now it depends upon the value of m. First, that you know that m is equal to x by h, it should be less than equal to 0.4. If it is a less than equal to 0.4, you calculate the n value is equal to z by h. If it is a m value x by h is less than equal to 0.4, then you adopt this equation, that is sigma h is equal to h square by Qp is equal to 0.28 n square divided by 0.16 plus n square whole to the power q. Case 2, if the m value greater than 0.4, then sigma h divided into h square by Qp is equal to 1.77 m square n square divided by m square n square whole to the power q. So, first of all, you have to calculate that what is n. N is equal to z by h. Also, you have to calculate m. M is equal to x by h. You know at what location the wheel is located from the face of the element. So, you can calculate that what will be the m value. So, m value is equal to x by h is equal to height of the wall. Similarly, you can calculate the n. So, you know at what depth you are considering z, and you know h is equal to height of the wall. So, first of all, you should calculate what is m and n, and then you check whether m value is less than equal to 0.4 or m value is equal to greater than 0.4. So, depending on that, then you can select that what will be the sigma h value that you can calculate. So, this you should know. Now, here is showing some calculation, that is stress due to the wheel 1 and 2. So, we are considering the stress due to wheel 1 and 2. Let us say that you want to calculate that what will be the location for stress. This is wheel number 1, this is wheel number 2, and we know that what will be the z, that is height of the wall. This start from 1 to 8 meter height. So, you have to calculate what will be the n value. We know that n value is equal to z divided by h. So, you consider the z at different depth, that means 0, 1, 2, 3, 4, 5, 6, 7, 8 up to 8 meter. For example, that z value is equal to, you are assume that z value is equal to 2. So what will be the n value? Because height is known is equal to 8 meter. So n value will be equal to z divided by h. That means what is z? Z is 2 meter. So this is 2, this divided by 8. So this n value will give you is equal to 0.25. So for any depth you can calculate that what should be the n value. And x is given 1 meter from here to here. This is x is 1 meter. And you know that m is equal to x by h. So if x is equal to 1 and h is equal to 8, so m value will be equal to 0.125. 0.125. So this m value is 0.125. Now you check the equation. So you check this equation that whether m value is less than 0.4. If it is less than 0.4, in our case m value is less than 0.4, so you adopt this equation. That means sigma h into h square qp is equal to 0.28 n square by 0.16 plus n square whole to the power q. Now you know what is the n value. N value is known 0.25. You can substitute n value 0.25. Then you can have sigma h by h square by qp. So if you know sigma h into h square by qp is equal to some value. Okay. Let us say for 2 it is a 1.59. So h is known 8 square and qp you know for that wheel is 25. That is 25 kilonewton. So you can calculate the sigma h for the wheel. Let us say we want to calculate for this wheel number 1. So you can calculate that what will be the sigma of h for the wheel number 1. So I am showing you this here, the chart, that this is the z, this is we are calculating stress due to wheel 1 and 2. So this is the z, this is 8 meter height wall. So 1, 2, 3, 4, 5, 6, 7, 8. So n, as I say that z by h. So at any depth z, when it is 2 meter I said, and h is 8 meter, so z you can calculate 0.25. Like this you can calculate what is n value at different depth. And x I say this is 1 meter. And then m is equal to x by h. X is known, height is known 8 meter, so this is 1.25 is constant at all depth. Now we know that because this m value is less than equal is 0.4, so you adopt this equation. I say this equation we have adopted. That means sigma h by h square qp is equal to this. N value is known. So you can calculate this. So this you have calculated. For let us say 2, you have calculated 1.59. Now for the wheel 1, so sigma h you have to calculate. That means sigma h will be equal to 0.62 because h is 8 and qp is 25. This is for wheel load, it is given 25. This is 25 kilonewton qp for wheel 1. So when you calculate for wheel 1, this is 25. So you can calculate sigma h by h square qp from this equation, you will have some value. So you can calculate what is sigma of h for wheel load 1, suppose 0.62. When you calculate for what will be the wheel load 2, so wheel load 2, you can see that this is wheel load 2, and which is making at an angle of 54.5 degree. This is wheel load 2. Here also QP is 25 kilonewton, and it also located at a 1 meter here. So for this angle, you can adopt this equation, that sigma h dash is equal to sigma h into cos square 1.1 theta. So, you know that what will be the theta value, this is 54.5 degree. So, you know 54.5 degree, this is theta. Sigma h is known to you, you have calculated from here, that sigma h. So, sigma h dash will be sigma h into cos square into 1.1 theta, and theta is known, that is 54.5 degree. So, you can calculate what is sigma of h dash. So, knowing this value, knowing the theta value, so you can calculate this, what is sigma h dash kilopascal for the wheel load 2. So, I think that you have some idea how to calculate the stress for the wheel load 1 and corresponding the wheel load 2. So, later on we will also discuss for the other wheel load 3, 4, 5, 6, 7 and the 8, and we check up what will be the pressure, and we will also check up what will be the relationship between the depth and pressure, how it is increasing and it reaches to the maximum value and then it is decreasing, and what depth it can give that maximum lateral pressure. That we will check up with this example. So, I think that we have some idea about the reinforced soil retaining wall, and also you have some idea if there is a wheel load, that also you have to be taken into consideration into the design, apart from the static load, dynamic load, seismic load, also wheel load you have to take into consideration. With this, I ended up this lecture today. Let me hear from you any question. Thank you for listening.